All right, so we know this is labeled as gases, but as we look at this, we'd see some things that would be a clue that maybe we're talking gas. We got volume, temperature, and pressure, all within that opening paragraph. It's talking about flasks that are sealed. And then we kind of give an overview of the different parts here. Okay, is the pressure greater than, less than, or equal to? Pressure, that's our clue. We're talking either gases or equilibrium, and we see greater than, less than, equal to. That means it's going to be in our best interest to make a guess here. KMT, 2 reasons. Okay, we're talking about how particles are moving, and we're looking at temperatures here. Okay, a second experiment, we're mentally getting ready for something else. We've got a reaction, we've got some graphs, we're thinking about order, and then we come back and talk about final pressure here. So we're kind of going back and forth. I mixed this one had some kinetics mixed in that I like, that was quick and easy, because you're going to be moving back and forth between those things in your head. So was the amount of liquid ethanol in the flask, when the amount is constant, is the pressure greater than, less than, or equal to 100? Okay, the vapor pressure, we are told it's 35. The liquid initially decreases, it stays the same there. It's got this boiling point, it's got this vapor pressure. So as we read all of that, what we would wrap our mind around is that, okay, we are not yet boiling, it has an equilibrium vapor pressure. If we have the same amount of liquid there, we're going to be keeping the same amount of ethanol. So it is equal because we are going to get to that equilibrium. And as long as we are not making any other changes to our flask, opening it, closing it, or changing temperature, that's how much we would have. The flask is heated. Okay, faster moving particles. That's what we think, especially since it says kinetic molecular theory. 2 reasons that the pressure is greater. 1, the particles are moving faster, they collide with more energy. 2, the particles are moving faster, they collide more often. The 3 on this is when it gets hotter, more of the liquid evaporates, so there's more particles as well colliding more. So there's 3 answers here, but temperature means faster, faster means more collisions, and more energetic collisions. So that's how we can get those 2 fairly equal fairly quickly. Another experiment, we've got a flask, we've got ethanol, we've got a copper catalyst. This is happening. We're looking at our concentration over time. Given the reaction is 0, 1, or 2, use the information to determine the order. Well, this is concentration versus time, natural log versus time, reciprocal versus time. Super important that you're reading the y-axis here, because they're not always going to put them in the quote-unquote right order. It's also important to remember that we start counting at 0. So this would be, if concentration's linear, that's 0 order. If natural log is linear, that is first order. When reciprocal is linear, that is when it's second. So this is first order, which means, or excuse me, 0 order. I just fell into my own trap, which means the rate is just equal to K. Changing the concentration doesn't change this. So that's a weird thing. I could put more in, I could take some out. The rate is not dependent on how much ethanol I have there. It just happens. If there's ethanol there, it happens. So that rate law is a good tricky one that they're going to mess you up on. It's just rate equals K. The pressure at the beginning is 0.4 atmospheres. If the ethanol completely decomposes, what's the final pressure in the flask? So what we would think about there is you might be tempted to look at the data here, to look at molarities and all of those things. But it's really a stoichiometry question with gases. So I had 0.4 of this. When that breaks down, it breaks down to 1 of these and 1 of these. So if I have a mole of this, I get 1, 2 moles. Or if I have 0.4 moles, it would be 0.4 of this and 0.4 of that, sorry, which also connects to my atmospheres. So my final is 0.8. So when going through questions, pressure, volume, temperature, we didn't have to do any math, but we were still talking about a gas. New pressure, still no calculations, but talking about how the particles move. KMT is a good clue. We're talking about that. We're paying attention to labels on these. We are kind of taking our time. We're mentally going back and forth. And then we're remembering right here that gases, equilibrium, kinetics, every single thing still comes back to stoichiometry. So even though it's taken us a whole bunch of different directions here, it is a 1-to-1-to-1 or 1 mole creating 2 total moles problem that makes this one important to be able to answer.